that. I disconnected and called back in. So if there's any audio issues throughout, please let me know.
We will.
So sorry for that delay, but hello everyone. My name is Kevin Robbins, and I'm a product marketing engineer on TI's position sensing product line, which encompasses our magnetic Hall effect sensors. Today, we'll be talking about one of our newly released Hall effect sensors, our TMAG 5273, and this device is a low power linear 3D Hall effect sensor. So quickly jumping into our agenda for today, I'll go over our current linear Hall effect sensor portfolio, along with highlighting our multi-axis linears. I'll give a quick overview showing the differences between single axis and multi-axis sensors in case you are not familiar. And then we'll dive into the TMAG 5273 overview, along with some example applications and tools to get started. If you have any questions throughout, please message McCrae in the chat options. He's an applications engineer on the position sensing team, and he will be available to answer questions throughout. Okay, so taking a look at our current linear Hall effect sensor portfolio, all of these devices are available on TI.com. On the left-hand side, you'll see our existing single-axis linear Hall effect sensors, and on the right half, you will see our multi-axis offerings. So like I mentioned, today we're going to really highlight the 3D linear Hall effect sensors, but our single-axis offerings are also available on the web. So you can find the TMAG 5170 and TMAG 5273 on our multi-axis linear and angle position sensors page on TI.com, along with some other resources. The TMAG 5170 is our high precision linear 3D Hall effect sensor that uses SPI. This device, along with the automotive version of this device, can both be found online, and today we'll be focusing, like I mentioned, on that TMAG 5273. However, if you are interested in the TMAG 5170, there was a webinar that was recorded back end of October in 2021, and you can find that on the ti.com/NPU page under the Hall Sensors webinar. So you can find some great information about those devices along with some additional details that I won't go into too much depth today. So starting off with reviewing the concept of single-axis linear Hall effect sensors. So these 1D sensors output a signal that's proportional to the magnetic flux density. And so these devices are sensitive to a single axis of sensitivity. Typically, it's what we call the z-axis, and usually that means they're sensitive to magnetic fields that are perpendicular to the surface of the package. And so you have usually two different options. So you have what's called bipolar sensors, which is shown on the left. And these single axis linear devices, like our DRV 5055, which is an analog voltage output device, and our DRV 5057, which is a PWM output device, they produce unique outputs for both the north and south poles of a magnet. So these bipolar devices work well in applications where the magnet moves from the right to the left or vice versa above the sensor. Whereas unipolar devices, like what you see on the right side, like our DRV 5056, which is also an analog voltage output device, are sensitive to only one pole of the magnet. So unipolar devices work well for applications that have a magnet that's moving up and down directly above the sensor. And an example of that would be this cordless power tool trigger as shown on the far right, where you can see the magnet, the travel direction is in line with that TO92 through hole package device. Although linear one-dimensional sensors are suitable for a variety of mechanical arrangements, the nature of the magnetic field of a magnet is not one-directional, so it can sometimes be difficult to achieve, perfect alignment in every system using a one-dimensional device. So that's where our multi-axis linear Hall effect sensors come into play. So three-dimensional or 3D sensors enable absolute position measurements, and they give you a high degree of flexibility in the device functionality and the sensor placement in your system in relation to the magnet. So you're getting a lot more mechanical flexibility as well by using a 3D linear Hall effect sensor. So these sensors integrate 3 independent Hall elements in a single package. So for the X, Y, and Z axes, and so they're sensitive to all 3 instead of just a single axis like with the 1D sensors. So again, you're getting added flexibility in your sensor placement, which is a huge benefit for systems that have limited mechanical space in order to align your magnet and your sensor. 3D linear sensors like the TMAG 5170 and TMAG 5273 are also capable of calculating angle and magnitude for any 2 axes, making the device ideal for both rotational angle measurements and for monitoring linear position with just a single IC. So I'll talk a little more about comparing 1D sensors and 3D sensors with an angle measurement example here. So just to give a quick comparison to show some of the added flexibility you get with a 3D sensor. So for instance, in this angle measurement example, in order to detect 360 degrees of rotation by using single axis linear sensors, as you can see on the left, you would need to use 2 sensors and they would need to be placed adjacent to the magnet and they would need to be 90 degrees apart from each other. So this implementation can add some added mechanical limitations to your design. So if you have limited physical space in your design, you could have sensor alignment errors. And then also you could have sensor alignment errors that occur during board assembly as well. So you have more room for error by using the single axis linear implementation with 2 devices. Now, if you're using a 3D linear Hall effect sensor, as you can see on the right, you'd only need a single IC to detect 360 degrees of rotation. So it allows for intrinsic 90-degree alignment inside the device package, and so that gives you that flexibility in sensor placement, which is unlike the 2-chip implementation using the single axis linears. So the 3D implementation can help you reduce physical space requirements while also offering that added mechanical flexibility, and you don't have to worry about alignment from channel to channel. The 3D sensors implementation also typically has better sensitivity matching versus the two-chip implementation, and that enables you to have better and more precise angle measurements, which is important in a high-performance system. And 3D sensors also are typically in surface mount packages, so you don't have to worry about a through-hole package such as a TO92, since that package is typically more expensive, larger, and has a more complicated board assembly process typically. So you're also getting that ease of assembly by using a 3D linear Hall effect sensor. And another major benefit of a 3D linear Hall effect sensor, such as the 5170 or TMAG 5273, is the Integrated Angle Coordinate Rotational Digital Computer, which stands for CORDIC, and that calculates both the angle and magnitude on chip. So performing this calculation on the device eliminates the need for post-processing the magnetic information. And so that integrated CORDIC provides the full 360-degree angular position information for both on-axis and off-axis angle measurement topologies. So what's shown here is on-axis topology, but if you have, again, depending on your mechanical setup, if you have limited space and you would need to have an off-axis setup between your magnet and sensor, you could do that as well with the 3D linear Hall effect sensor. So the angle calculation is performed with using 2 user-selected magnetic axes out of the 3 that are available. The third axis can actually act as an additional input source to initiate an interrupt to the system. And that can alert the system to events such as tampering or whatever else you set that event to be to alert your system. And so we'll discuss this a little bit more in upcoming slides. And the last thing I wanted to mention here was that the device features magnetic gain and offset correction as well. And so that helps mitigate the impact of system mechanical error sources, which again, you're not getting from the single axis linear implementation. Now, just to get into a quick overview of the TMAG 5273, as I mentioned, this is our low power linear 3D Hall effect sensor with I2C. And this device has a dedicated interrupt pin, and this pin can act as a system interrupt during low power wake up and sleep mode, and it can also be used by a microcontroller to trigger a new sensor conversion. So we'll discuss the dedicated interrupt pin in the next slide as well. This device also has numerous power modes that you can use, which includes wake up and sleep mode, where the device is placed in a sleep mode and then wakes up at specified intervals to take measurements, and multiple intervals are supported so that you can really maximize your throughput versus power consumption depending on your system needs. As I mentioned, it has that integrated Cordic angle calculation for that 360-degree angle position information for on or off axis measurement topologies, and all of that's calculated on chip using 2 user selected magnetic axes. Let me remove that notification. Okay. And like I mentioned before, also the device features magnetic gain and offset correction. You also have the choice between 2 different device versions, so the TMAG 5273A1 version and the TMAG 5273A2 version. So that gives you the choice between 2 independently selectable X, Y, and Z magnetic ranges, depending on which device you choose. And this device also supports supply voltages down to 1.7 volts as well, which can be very beneficial in battery-powered systems. So we only have, 30 minutes this morning, so I won't have time to highlight all the great benefits of this device, but the data sheet that you can find on the product folder on ti.com goes over all of the features extensively. So please take a look at the data sheet as well. But just to give a quick summary though, this device has numerous configurable features that can help you set it up to meet your unique system requirements and provides you with that added flexibility and sensor placement within your system. Moving along to the dedicated interrupt pin. So the TMAG 5273 is offered in a 6-pin SOT23 surface mount package and has the I2C bus on the SCL and SDA pins, but then also has that dedicated interrupt pin. So the dedicated interrupt pin can act as a system interrupt during low power wake up and sleep mode, and can also be used by a microcontroller to trigger that new sensor conversion. So the device wakes up periodically to take some measurements and then only wakes up the microcontroller through the interrupt pin if a predefined threshold on the X, Y, or Z axes or threshold on the temperature sensor is crossed. So the dedicated interrupt pin also gives you some added flexibility when actually alerting your system to an interrupt. So you have multiple user-defined interrupt and conversion trigger functions on this device, so you do not have to use that interrupt pin. However, you do have the option to use that interrupt pin, or you can use the I2C line via that SCL pin for the interrupt signal. And so that gives you also some added flexibility if you don't have an extra GPIO for that to use that dedicated interrupt pin. So the first options you have for the interrupt signal is a fixed width interrupt signal. So you have that signal can be used on the dedicated interrupt pin, as you can see on the left, or on the SCL pin via the I2C communication, as you can see on the right. So that fixed width interrupt signal is a 10 microsecond signal that is alerted or that is asserted when a magnetic threshold is detected, cross is detected. And so it'll assert for 10 microseconds, and then the device will go back to standby mode. So again, you could do that via I2C or via that dedicated interrupt pin. Your third option is to use the dedicated interrupt pin to assert a latched interrupt. So this option allows the user to determine when to clear the interrupt signal if you do not want it to be asserted just for that 10 microseconds. So when a magnetic threshold cross is detected, the device will assert a latched interrupt signal, and it will stay asserted until the microcontroller clears the interrupt and goes back to standby mode. So the dedicated interrupt pin allows for faster interrupt resolution, and it doesn't interfere with the I2C communication. Whereas, if you use that SCL pin with the fixed with interrupt, you could interfere with that I2C communication. That dedicated interrupt pin, like I mentioned, does require an additional GPIO in addition to the two standard I2C bus lines. So if you don't have that added GPIO, you still have options to implement an interrupt signal. So again, multiple options to fit your unique system needs. And as I've also kind of alluded to, this device has multiple programmable thresholds that can be used for tamper detection or to reject stray fields when they're present. So you can set independent thresholds for the X, Y, and Z axes. They can all be different, and also for the temperature channel, since there is an integrated temperature sensor. So these thresholds can be used in a variety of ways. So thresholds can be set to alert the system of tampering or excess stray magnetic fields that would interfere with normal operation. So for instance, if you're using two axes, let's say for angle measurement, you can use the third axis as an additional input source, and that can be used to initiate an interrupt. So for the axes being monitored, you can set the threshold to a value just above what you would normally expect or what you set as an acceptable input. And so when the field exceeds that limit, you can be sure that some outside source is influencing performance and should be rejected. So it would, if you cross that threshold, you would know, hey, this is a abnormally large external magnetic field that's trying to tamper with, say, an electricity meter and steal electricity from the grid is one example. And the on-chip temperature sensor monitors the temperature of the die and compares it to a user-defined threshold as well. So the system will be alerted of a thermal failure without the additional cost of an external temperature sensor. So it's just kind of another added benefit as well, and another programmable threshold that you can utilize to help protect your system. So the TMAG 5273 has numerous configurable options again, so it gives you maximum flexibility. And there's just a quick summary here, but again, the datasheet has a full list of all of the different configurable options. As I've mentioned, you have that the two choices between the selectable linear magnetic ranges. You have numerous conversion rates that are supported as well, depending on the performance versus power consumption needs of your system. And then you also have the option to use temperature compensation. So as temperature increases, the magnetic field produced by magnetic materials weakens. So this predictable behavior can be compensated for by the sensor, and that can help provide a flatter response for more reliable performance. The TMAG 5273 offers 3 temperature compensation options. So a 0 temperature coefficient option, or 2 other options, one for neodymium magnets and one for ceramic magnets. You also have numerous wake up and sleep mode intervals. And as you can see in the table on the bottom right, that's just kind of a quick example of some of the different sleep intervals and their average current consumption, whether you use the temperature sensor in all 3 channels, so the X, Y, and Z axes, or if you use the temperature sensor and just a single axis, you can compare, some of the average current consumption values to really utilize that low power functionality. And then you also have configurable averaging for up to 32 times for noise reduction. And so again, just highlighting here that this device is extremely configurable and can really fit in your system. And so you don't have to fit your system around your position sensor. Getting into some example applications. So the first example here would be electricity meters. As I mentioned before, you can use this device or 3D linear Hall effect sensors for magnetic tamper detection, or what we also call 3D limit detection. And so you can use this to prevent energy theft. So you could set one or more of the device thresholds to detect abnormally large magnetic fields. So when the field exceeds the predefined limit for any of those axes, you can be sure that that outside source or some outside force is influencing performance and should be rejected. Magnetic tamper detection is not only applicable to electricity meters, door and window sensors and other applications as well are also needing magnetic tamper detection more and more recently. So if you need to detect large external magnetic fields, and for instance, for door and window sensors, people are now taking a large magnet and holding it up to the sensor to essentially open or close that door without the system um, realizing. So for door and window sensors, the device can be used for open and close detect or magnetic tamper detect as mentioned. So simple switches like Hall effect switches or other types of switches can be used in door and window sensors for open and close detect as well, but they do require precise installation, which is not realistic in this day and age for these systems that are consumer installed. So for instance, if you have user installation error as shown here, where the magnet is off center from the sensor, it's not aligned properly, a 3D linear Hall effect sensor can still account for this off-axis installation and still perform as intended. Another example of a non-ideal setup would be a raised door trim or raised window trim as shown here. So again, if you use a simple Hall switch or other type of switch, you may have some issues accounting for these raised door trims, whereas a 3D linear Hall effect sensor can still accurately monitor these scenarios as well. Next example, we have electronic smart locks for angle measurement or absolute position of the bolt shaft, also magnetic tamper detection as well. And then down in the bottom left, we have our HMI knobs. So these human machine interface control elements, such as knobs, can be on thermostats, appliances, or stovetops. So the knobs can be used to adjust the temperature setting on a thermostat, select the settings on a washer or dryer, or to adjust, the cooking temperature on a stovetop. So compared to a mechanical-based approach, 3D linear Hall effect sensor implementation is contactless, so you'll have less issues with wear and tear. And then if you compare using a 3D linear Hall effect sensor for knobs compared to using Hall effect latches, which is also another common implementation. A 3D linear Hall effect sensor can detect when the knob is pressed or pulled with one IC and detecting the rotation of that knob as well. Whereas with another solution, you would not be able to do both of those functions with a single device. And in addition, you'll have finer resolution measurements with a linear 3D Hall effect sensor without requiring as many pulls on a magnet like you would with a latch setup. And lastly, as you can see here as well, joysticks. So you could do 3D absolute position and multi-state detector measurements for joysticks. So again, a single IC for push or pull and for the 3D absolute position measurements as well with a single device. So these are just a handful of applications, but this device is extremely versatile. Again, that low power operation really makes it ideal for not only connected systems, but wireless systems as well. And so lastly, I wanted to highlight some tools and resources for you to get started if you're interested in learning more about this device, or other devices, or starting some initial evaluations. So I have links here for the product folder where you can find the data sheet and additional technical documents, videos, design files as well. I also linked the EVM here. So the EVM comes with a 3D printed rotate and push module, so you can test out that functionality I mentioned of rotate and push using a single IC. However, we also have other design files online and user's guides for our other supported 3D print attachments. And so we have what we call a slide by attachment, joystick, a head-on linear, and orbital attachments that are all linked here and can all be found online on ti.com as well. You can find these files on the product folder along with the EVM tool folder. We also have an EVM getting started video that McCrae put together that will also help you get started with the EVM and using the accompanying GUI as well. Our Magnetic Sensors TI Precision Labs video series offers some great videos that discuss all types of Hall effect sensors, so switches, latches, single axis linears, and 3D linears, in case you want to know some additional details about that are more in depth about specifications of these devices and example applications. I also put this tamper detection video down since I do highly recommend that video since it does showcase some of the magnetic tamper detection features of this device. And then some accompanying documents below, and then also our magnetic sensing proximity tool, which can be found on all of our Hall effect sensor product folders and is an Excel-based tool that is really great for getting started with any of our Hall effect sensors. And lastly, again, please visit the ti.com/NPU site for any of our pre-recorded sessions, along with the Hall Sensors webinar that was held back in October of 2021. That includes the TMAG 5170 in a lot more detail as well. Thank you all for attending, and I hope you all have a great day, and please reach out if you have any further questions.
Thank you so much, Kevin and McCrae. If anybody has any last questions, feel free to pop them in chat. We'll stay on the line for a minute more. And if not, we'll see you next week or the next time you join. Thanks, Kevin. Thank you, McCrae.
Thank you, everyone.
Thank you. Bye-bye.
Bye.